You're listening to a podcast from 702 and Cape Talk.
702 and Cape Talk.
The Naked Scientist.
All right, I don't know what time it is, but it is time for The Naked Scientist, and I want to start by thanking everybody who came out this morning. Give yourselves a round of applause. I'm particularly happy that you brought your children, your friends, because these are the future scientists, and I'm very happy about that. Thank you for coming, guys. Did Aki abuse you while I was away?
No. Oh, what do you mean, yes?
Yeah.
That's so not true.
Children never lie.
Can I abuse you, yes or no? Oh, that's nice.
Do you have a question for The Naked Scientist?
I do. I've got a couple of questions.
No, Aki. There's no time.
One question.
There's no time for a couple of questions. So we'll come to you. You'll be the last one to ask the question.
Thank you. Why am I the last one?
Because I'm hoping that there'll be no time to take your question.
Oh, thank you. Listen, I've got all the kids. They want to ask questions. I'm super excited. He's going to blow things up as well today. You know that?
Absolutely. So we're going to have these live experiments, as we always have every single year. And The Naked Scientist, of course, is brought to you by The Rand Show. It's showtime. What does that mean? If you didn't manage to make it here this morning, you're driving to wherever you're going, you still have an opportunity throughout the Easter weekend to go and see The Naked Scientist at The Rand Show, and we'll give you details about that. Chris, good morning. Welcome.
Good morning, Rudy.
It's lovely to be with you. And, of course, you never travel alone, hey? You don't know how to be alone.
It's the best way to be.
Okay, we've got Victoria Charlton. Victoria, you can tell us more about yourself and introduce yourself to 702 and Cape Talk listeners.
Hello, my name is Victoria. I'm a science reporter for the BBC, so I'm normally on the other side of the microphone asking questions of scientists. But sometimes I join in with The Naked Scientist and do a few shows like this. I leave Chris to answer most of I'm sure you're burning with questions to ask him. I'll leave Chris to answer most of those, but I have a couple of experiments that should show you some quite cool scientific tricks that hopefully a few of you will help me out with as well.
Thank you so very much. So, Chris, where do we start? What do you have for us?
Well, what I thought we'd do is to do some questions first, and then when you feel experimental, then you can invite Victoria to do a couple of things. We do need a bit of audience participation. You might lose the odd arm or two, but don't worry. Prime Media has good insurance, I understand. No, it's pretty safe. But we have got some things that do need a little bit of participation, and I've got some prizes for the best questions. So we're going to try and remember what the questions are, and we're going to pick the best ones, because I've got some Rand Show tickets to give away, and you've even got this wonderful chocolate bar. Look, I mean, that really must be the doyen of prizes.
That's a big prize, eh?
Yeah, that's a really good... Actually, what you don't know is that wrapped up in there's £1 million. So, no, just kidding.
All right, let's get going then. Who's got a question for The Naked Scientist? This is your chance to satisfy your curiosity. And where do we start? We start right at the back. Just speak up, give us your name, and let's get going.
Yes, here we go. A young man over here. Where are you from? What's your name?
My name is Zayden.
Where are you from, Zayden?
I'm Saturn.
Oh, okay. Thanks, Zayden. So, what's your question that you have for The Naked Scientists?
Does enormous magnets affect the human body?
Oh, that's a good question. So, you want to know if you put an enormous magnet next to you, what happens? Have you tried this on your sister? Okay. So, what happens when you put an enormous magnet next to you?
Well, actually, people do this every day in many cities all around the world, because actually we use very powerful magnets in hospital to get scans of people. They're called magnetic resonance imaging studies. And when we have a very powerful magnet, you put a person in that magnet, and it makes all of the water molecules, the hydrogen, line up in your body and spin in a certain direction. And this way, you can send a small pulse of radio energy into the body, and then the hydrogen atoms get knocked off kilter temporarily, and then they flip back in line with the magnetic field, and they give out a little signal of their own, which the scanner can pick up, and it can use that to build a three-dimensional image of the inside of your body. And that's a magnetic resonance image. But in general terms, our bodies are not affected by magnetic fields. So if you buy one of those bracelets that's magnetic and will improve your health, there's no evidence at all this is going to make any difference to your health. But there will be a placebo effect, because if you believe it's going to make a difference to your health, then it probably will actually make you feel happier and healthier, even though it's not doing anything to you. The really, really amazing thing, though, is that you can use a really, really, really powerful magnet to levitate yourself. And there's a guy called Andre Geim who got the Nobel Prize just recently for the chemical graphene, his work on that. But one of the things he did previously in his scientific career, and I think it actually won him an Ig Nobel Prize for doing this, was he put a frog in a very powerful magnetic field, and he managed to make the frog levitate, because you can actually make the atoms in the frog, the hydrogen atoms, spin in the way I've explained, and they give out their own magnetic field under those circumstances, which opposes the magnetic field that the frog is in, and so you get a levitation, and the frog began to float. You could also do it with a tomato as well. If you had a big enough magnet, you could do it with a human.
So what happens if you've got a pacemaker, for example?
Well, that would be bad news. You might not have a pacemaker for very much longer, and you probably wouldn't have a heart either, because any piece of metal that's potentially magnetic, if that goes into a scanner that uses a very powerful magnet, then the piece of metal will try and move with the magnetic field, and it will turn into a sort of inbuilt liquidizer, and it will pulp you in the scanner, which wouldn't be good.
We'd like to see that happening to Aki.
No, you wouldn't.
Maybe we can try that. All right, where's our next question
Here
coming
we go.
from?
We're going to go to the
Let's get
back.
going.
Who's got a question? Raise your hands, please. Right. What is your name? Where are you from? And what's your question?
Andrea, I'm from Rampart Ridge. I wonder if this is okay, but can I ask two questions? It's just two questions.
It's fine, it's all right. It's Easter, we have spirit.
It has to do with psychedelics. Now, recently I watched a documentary on marijuana, and often we hear in school, do not do drugs. Whatever you do, like, don't take them, and they're bad news. But then I found out that there's actually a lot of benefits. Like in Israel, they use marijuana to treat cancer and stuff, Alzheimer's. And then I started researching other drugs, and I came across magic mushrooms, which improve neuro pathways in the brain, and ayahuasca. I was wondering if you could expand on that, the health benefits to many of these psychedelics or just other drugs.
You need to spend more time doing homework.
Just as an aside, because you mentioned the sort of the drugs image and the drugs message, don't do drugs, drugs are bad. There was a company that made a pencil that said on it, don't do drugs. Now, the problem is that they hadn't really done their research and development. It's very important when you're doing science to do some appropriate R&D and check what you're doing. Because what they didn't do was to think, what will happen when I sharpen the pencil? Because as you sharpen the pencil, the don't do drugs disappears. And you get a pencil that says, do drugs! They withdrew it from sale quite quickly. To answer your question about drugs, you have to be very cautious how you interpret the word drug, because the fact is that of the things we give in hospital, I think probably 10% of the most prescribed chemicals used in hospital are directly derived from nature. We make those chemicals in plants, extract them, and then give them to people, or we make versions of them that are similar to what the plants know how to make. So just because something comes from nature, it doesn't mean it's bad, and it also doesn't mean it's necessarily good either, because these chemicals are very powerful and they impact on certain pathways in your brain and your body. What actually becomes a problem with drugs is when people use them to make up for a problem in their life. And these agents, like marijuana, they do have quite serious effects. And yes, used correctly, they can be very therapeutic for certain people with pain. They can be very good for people who don't eat properly because they've got cancer, and they can increase appetite, so they can help people to keep their body weight up. They can stop people feeling sick if they're on chemotherapy and things. If they've got other things like muscle spasticity, where you get muscle stiffness in diseases like multiple sclerosis, it can be really good for that. But that's in a certain context, given in a certain group of patients. For people using these things recreationally, there can be very, very serious side effects. And more recently, they've actually made or bred forms of the marijuana plant that produce very, very high levels of the psychoactive chemicals that people are using the plant for. And this includes the chemical THC, or tetrahydrocannabinol. And the problem with this is that unlike the natural form of the plant, where you had certain amounts of these chemicals present with other chemicals that counterbalance the negative effects, if you enrich just for one of those chemicals, you don't have those counterbalancing effects anymore. And there's a high risk of developing psychosis if you are exposed to these substances, especially skunk. And as a result, people can develop schizophrenia, and it's regarded as a risk factor for getting diseases like schizophrenia. And it sounds a bit trite, but there is this phenomenon of gateway drug taking, where if people take one agent that's regarded as relatively safe, then you tend to come into contact, because of the environment in which that's happening, with other agents that are relatively less safe, and that can lead to, in some susceptible individuals, progression to take harder and harder drugs. So yes, there are benefits of taking some of these agents in certain contexts, but used recreationally, they can have negative effects, especially on some susceptible individuals. Would you go along with that, Vic?
Yeah, there's a lot of social context around how these drugs are used. I think there's some really interesting studies. I think you were talking about magic mushrooms, and psilocybin is the hallucinogenic active ingredient in magic mushrooms. There's some really interesting studies looking at the use of psilocybin for post-traumatic stress disorder. And I think they make great stories, those kind of tests on very severe cases where people have something as horrendous as post-traumatic stress from, say, being a soldier in a war zone. But that doesn't relate to exactly all of the social contexts surrounding using that in a much wider setting for patients in general. So I think it's a big, complicated issue, and there's some very interesting stories in there.
Worth bearing in mind that the drug ecstasy was actually invented in 1914 by the Merck pharmaceutical company, and they invented it as a way of making troops who were going to war feel less hungry in the trenches, but unfortunately it had a side effect that they didn't really feel very much like fighting and killing people, because they just wanted to hug each other, so it got withdrawn.
Well, there are worse things in life than soldiers who want to hug each other. Where's our next question coming from?
Yes, who's got a question? By the way, as we come to the next question, if you're listening at home and you want to watch the stream, this is going out live on video as well, so you can watch us on the internet. And if you go to the 702 Facebook page or follow us on Twitter at Radio 702, just click on the link and you'll be able to watch this video live. What's your name and what's your question, young man?
Seth, I'm asking, why does popcorn pop?
Why does popcorn pop?
Because it can.
It's been selectively bred, actually, to have a certain characteristic that makes popcorn poppable. And there was a chap, actually, recently who published the first proper scientific treatise on the popping of popcorn. It's a French gentleman. And what they did was to put the popcorn in front of a very high-speed camera so that they could take 3,000 pictures a second of popcorn popping to work out exactly what's happening. And they found that you need a threshold temperature. You need the temperature to be 180 degrees C. 170 degrees C and only about 10% of the popcorn pops. 190 degrees C and all the popcorn pops. So at 180, that seems to be the turning point. What's happening then? Well, there's a little bit of water trapped inside the popcorn. The popcorn seed has got a very tough crystalline outer shell called the pericarp, and it acts like a pressure cooker. And when you get to that magic temperature of 180 degrees, the water inside, because under pressure the water can't boil and turn into steam, the water is driven into the starch, which is inside the seed, and it turns it into a sort of liquid state. And slowly the pressure goes up and up and up, and then at 180 degrees, that outer shell fails, and it pops open, and it allows the starch to begin to bulge out, and that's when the popcorn inflates. But you could ask, well, is that what causes the popping noise? Well, what they then did in their experiments was by taking those very fast video photographs and recording the sound at the same time, they asked, does the opening up of the seed, the pop, actually coincide with the pop sound that you hear? And the answer is it doesn't. What actually happens is that when it opens up and splurges the starch out to make the inflated kernel, the sound comes a little bit later. And what they found is that when it pops open, there's a big escape of steam from inside the popcorn pop. Bump. But it's actually, because that leaves a lower pressure inside the popcorn, it's the air rushing back in again, a tiny amount later, that then causes the popping noise. And it's very similar, the effect, to when you blow over the top of a bottle. If I take this bottle, it might be able to do it. If I blow over the top of this bottle, I've drunk some of the water out of it, so there's now a cavity above the water, and that can cause resonance, so you get a effect. The air rushing back inside the popcorn causes that similar sound with a wavelength corresponding to the size of the popcorn, which is why you hear the pop.
And you can see some of those videos online, actually. If you look up popcorn popping on YouTube, some of those high-speed videos where you can really see the moment where it pops, you can see those online. Have a look. It's really fun.
Gee, thanks, guys.
Great
Eating
question.
Popcorn will never be the same, Eric. You're like thinking about it as you're eating it. Crunch, crunch. Right, more questions. Come on. What is your name? You got your hand up so high. Is your mom the one that's got the e-toll and she doesn't pay for e-tolls? No.
Haki.
Why does Coke make you burp?
What do you mean? Was that you? That was disgusting. Did you just burp? All right.
The question up next is, why do Brussels sprouts make you fart? But we'll come to that in a minute. Why does Coca-Cola make you burp? Well, actually, any fizzy drink will make you burp. The reason it's fizzy is because people have put under pressure, carbon dioxide, which is a gas, into the liquid. So if you take a liquid and you force carbon dioxide into it under pressure, the carbon dioxide dissolves in the liquid. When you then take the cap off and it goes psst, like that, the pressure outside the liquid is lower for CO2, carbon dioxide, than what's dissolved in the liquid. So if you then actually leave the Coke standing, it will slowly bubble out. That's what the fizz is. And we like fizz because it actually imparts a little bit of acidity to the liquid. And when you put the liquid into your mouth, if you have a rough surface on your tongue, which you do, then that acts as what we call nucleation sites. You've got little bubbles form on all those little bumps, and it gives an interesting taste in your mouth. So we like it. That's why we make fizzy drinks. The problem is most of the bubbles don't escape when you put the stuff in your mouth. Most of the bubbles are still therefore hidden in the liquid, and you then swallow the liquid down into your stomach, and that's where the bubbles actually come out of solution, and they form a big bubble inside your tummy. And this increases the pressure in your stomach, and the response to relieving pressure in your stomach is you can either send the gas upwards or downwards. Most of it, which is in the liquid you've swallowed, therefore comes back upwards, and sometimes it can carry a little bit of what's gone down with it, so you can do a sort of wet burp. You're probably acquainted with one of those. Not terribly nice, not nice for the person next to you either. But that's the gas that's built up escaping, usually with tuneful effect.
We have another question here.
All right, here we go.
Aki, come to the front. You're discriminating against people who are sitting in the
people
front.
who sit in the
Let's
front are
start
people
here.
in class. They're the smart people. They don't need to know.
Yeah, you obviously never sit in front in class. Hey, some of us have had that experience.
Hello,
right?
what's your name? What's your question?
My name's Deborah. I just want to know, does Wi-Fi make you sick?
Wi-Fi.
Ooh, remember we had this last time, like cellular signals.
Oh, yeah, and we actually had said we'll ask the naked scientist, but you forgot.
Whenever we talk about cell phones, people think, oh, it causes brain cancer and Wi-Fi is dangerous. And
what's the science, Chris?
Yeah, exactly.
Well, Wi-Fi uses microwaves. Microwaves are part of the electromagnetic spectrum. That's light to you and me. And there's a very big range of what light is. It ranges from very long waves, which can be miles in wavelength, or kilometers to be metric in wavelength, and radio waves are an example of that, right through to gamma rays and X-rays, which are really, really tiny waves. And as you get tinier and tinier waves, they become more and more powerful or more and more energetic. And you reach a point where those waves are what are called ionizing. They have enough energy to physically break the bonds in a chemical. But the kinds of waves that are used in Wi-Fi, microwaves, and actually in your microwave oven in your kitchen, those waves do not have enough energy to break the bonds between atoms. And so where we think that radiation is damaging is when it can break the bonds in your DNA, and it can cause your DNA to rearrange itself, and that will cause cancer. Because there's not enough energy in the waves to rearrange your DNA in your cells from a Wi-Fi signal or a mobile phone signal, or actually a radio signal, thank God for anyone listening to Talk Radio 702 this morning, then you won't get sick because of that. So we're comfortable that these things are probably safe. That said, there may be other effects that we haven't yet measured. In other words, you know that when you put food in your microwave oven, it cooks your food. We know that when you use a mobile phone for an extended period of time, it does cook your brain, in the sense that there is an elevation in brain temperature on the side of the head where you're using the phone. Does the increase in brain temperature carry with it a risk of something else going wrong in your brain? That we don't know.
Aki's starting to look nervous because he's always on the phone. He's always on the phone and he always has a gadget.
Yeah, you're on your phone. You say our brains are actually being cooked.
Yeah, I suppose they are. It's not cooked very well, but thankfully. I certainly like my food well done. But,
so let me ask you this question. So would you advise people to use a hands-free instead of holding the phones next to their heads?
Well, the guidance is that for little kiddies, you should be more cautious, because as you get older, then you do become quite literally more thick-headed, because the skull is a lot denser in a bigger person than... Stop those silly hands, that's naughty. The skull becomes a lot thicker in an older person than a younger person. So a little child has a much thinner thickness of bone between the outside world and the brain tissue. So therefore the relative penetration of the energy from the phone going into the brain is going to be higher in a young person than an older person. And therefore there might be a difference in vulnerability. There will certainly be a difference in dose. So probably age is more important. Once you're a full-grown adult, you're probably getting a lower dose of the radiation than a child would. So maybe children should be more cautious than adults.
I think there might be is quite an important caveat, though, isn't it? Because the science is still ongoing. They're still taking a lot of clinical measurements of this and trying to figure out just exactly what is happening and whether there is a risk. So I think those are sort of studies to come out because the technology is still quite new.
Yeah, absolutely. It's only been around for like 2 decades, 3 decades. Okay,
Yeah,
more questions. Here we go. We'll go right to the front. The good kids in the front. What's your name and what's your question?
My name is Leia, and my question is, if you were to see a building from outer space, like from Australia, for example, would it be sticking out? Or what would it...
Oh, you mean like sideways, depending on the angle that you look at it. So how do buildings shape up when you look at them from outer space?
Yeah, effectively they would, because if you think about it, here in the southern hemisphere in South Africa, buildings go upwards, whereas if you go back to London and you think, why aren't these people in South Africa upside down? And the thing is, the Earth's surface is curving so gently, it's ever such a gentle curve, that where we stand on the ground, we regard that curve as almost flat for us. But we know there's a curve there because you can see boats disappearing over the horizon. And there's a little rule of thumb, if you want to know how far it is from where you are to the horizon that you can see, it's called the 1-2-4 rule. And you take the height of your eyes above sea level in feet, and you times that by 1.24 times the square root of the height of your eyes in feet above the sea. And that will tell you the distance in miles to the horizon, roughly. Just in case you're interested.
All right. Hello, what's your name and what's your question?
My name is Mohammed. My question is, when you get fever, why do you feel cold but you're actually hot?
I've been wondering about that for a long time myself.
So when you have a fever, why is it you feel absolutely freezing cold and shiver, but you're running a high temperature? Well, first of all, why do you get a fever in the first place? When we get infected with bugs, whether they're viruses or fungi or bacteria or some parasites, they're releasing chemicals into the bloodstream and triggering your immune system to release chemicals into the bloodstream that tell your body, I've got an infection. This goes to your brain, to a region of the brain called the hypothalamus, which controls it's your thermostat. It controls your metabolism and says, this is how hot you should be. And those signals tell the brain, make the body hotter. And there's a couple of reasons for this. One is that some chemical reactions run faster when they're hotter, and this includes some of the chemical reactions that the immune system uses to deal with infections. So it benefits the immune system to run the body a bit hotter. But because your thermostat's been turned up, your body thinks it's cold even though it's hot. So it then makes you think, whoa, I feel freezing cold, even though you're actually running a fever because you've turned the thermostat up saying I need to make the body hotter. And what it does is it increases your metabolic rate, so you're burning more energy and turning more energy into heat to run your body hotter. And this is advantageous for you and disadvantageous for the microorganisms.
Right, I think it's time for a break. I see all your hands, and then when we come back from the latest EWN, we'll be ready for an experiment. What do you think? You're right?
Absolutely.
Let's take a break.
702 and Cape Talk.
The Naked Scientist.
5 minutes past 10 o'clock, the second hour of the show. Thank you very much for staying with us. We are not taking calls, by the way, during the show with the Naked Scientist. Not that we don't love you, but suppose we're giving priority to those people who got into their cars this morning to make this occasion a success. So thank you again. The Naked Scientist coming to you in front of a live audience. And I can understand there's something about streaming and gadgets and things that I don't know anything about. If somebody can't be here but they want to watch, what's the story?
Yes. Well, listen, if you don't believe us that there's a live audience here, listen to this! Exactly. Now, you can see the live audience. Just go to 702.co.za and you'll click on a link that says live streaming. You'll go to our Cape Talk website, 567 capetalk.co.za. There's a link to the live streaming and you can see us right now. You can see how gorgeous Reedy's look.
It's not complicated.
It's not complicated.
How many things do you click before you get here?
You're complicated. That's not complicated.
The Naked Scientist is brought to you by The Rand Show. It's showtime. Chris, let's start with the experiment. Everybody's insurance papers are in order. What's our first experiment? What are we going to see next?
Victoria.
Right. First experiment is, do you all know how an airplane wing works? Hands up who knows how an airplane wing works. Quite a few hands up. So do you think we can show how an airplane wing works with a ping pong ball and a straw? Yes? Yes? I can't hear you. Well, to do that, I'm going to need some help, and I promise you that this can be achieved. So I need 3 volunteers. So I think your hand went up first. You in the stripy top. Do you want to come up here? What's your name? Tell Aki your name.
Zaid.
Zaid?
Are you nervous?
Right, I'm going to get you to stand up here on stage and I'm going to give you your experimental setup, which is this straw. So we've got a bendy straw. I need you to hold that and in your other hand hold your ping pong ball. And if you just wait right there for me, I'm going to get the rest of our volunteers. So I need 2 more volunteers.
Do you want 2 more volunteers? Who wants to join Zaid up on
This young woman
stage?
at the back here?
You go. You can come up. All right. Come up. What's your name? Maida. Okay, go up on stage. Don't be afraid of Reedy. She won't fight you.
Your hand also went up.
So we need a big
Here we go.
volunteer with big lungs, non-smoker who plays sports.
Right, there we go.
We need someone with really strong, powerful... Have you all got strong, powerful lungs? Yeah? We have some hesitation there. Okay, I'm going to give you all a straw. So in that case, Aki, I think I'm going to get you to take part in this experiment. Because you look like you've got pretty good lung capacity now. Let me give you that and that. So everyone's getting their bendy straw and 1 ping pong ball. So hold on to those. Have you all got a ping pong ball and a straw? Right. Aki, you get a beautiful shade of pink straw and a ping pong ball. And let me try to show you how this works. And I may have to turn to Chris, who can do this experiment beautifully. But basically, what we're going to do is we're going to make this ping pong ball hover over the end of this straw. We're going to make it bob up and down over the end of this straw. So we're going to blow as hard as possible through the straw, and when there's a really strong stream of air blowing through that straw, drop the ball right over the end of that stream so it's right in the middle, and you should be able to keep that ping pong ball hovering. So we're all going to have a go all at once. So after 3, you ready? We want to count us in?
1, 2,
3. Deep breath!
What just happened?
Right, Chris, come and join us. Well done. Let's get Chris up on stage to show you how this works beautifully.
Okay, Aki's
got it working it, but he is actually holding the ball. Slightly cheating.
So Chris is going to show us.
I'm putting the straw in my mouth like I'm smoking a pipe. Not that I do, but if I were to smoke a pipe, put it in my mouth, really deep breath, and I'm going to blow really hard down the straw and then drop the ping pong ball over the end of the straw, which is pointing up at the ceiling. So I've bent it up. Ready?
Whoa! Gee, that's amazing. You're a magician.
So did you all see that? Right. Okay, Aki, I'm going to get you to keep demonstrating that to the cameras while I explain what's going on. Deep breath.
1,000 rand prize to whoever can do that for a minute.
If Aki faints, I may need some more volunteers to come up and catch him. But you can just demo how this works. Right.
Deep breath.
Balancing the straw in your hands doesn't count.
So blow really hard.
Yay!
Well done.
So what we've got is this ball bobbing up on the end of that very, very thin stream of air on the end of that straw, right? So this is just a little bendy straw that you would get in a drink. And so that's a very thin stream of air that you're blowing through the end of that straw. But there's an effect called the Kokanda effect. All that means is that air will stick to a curved surface. And because this is a symmetrical curved surface, a completely symmetrical spherical ball, that air will actually stick to the outer surface of that ball and it will go all the way around it. Now, what that means is that when the ball moves to one side or the other and tries to fall off that little stream of air, it will drag that air with it that's stuck to its surface. And does everyone know Newton's laws of motion? So does someone want to shout? Gentlemen here, you put your hand up straight away. What's Newton's third law of motion? That's the first, I think. So it's the equal and opposite reaction. So every action has an equal and opposite reaction, right? So when this ball tries to fall off that stream of air and drags that air with it, that air exerts a force in the other direction to keep it back on the top of that straw. So you get it hovering beautifully, just as Aki showed us so beautifully. Are you guys having any more success? Come on, keep going, keep having a try. Don't faint. Need to blow really hard.
The ping pong ball's going all over the place.
So this ping pong ball is actually showing us what happens in an airplane wing. As the airplane flies through the sky, it goes through the air and its wings have that curve. You can see that curved shape when you've flown in an airplane. So, as it passes through the air is pushed down on the underside of that curve, on the underside of that airplane wing. And as the air is being pushed down, it exerts an opposite upward force on that wing. Now, over the top of the wing, because it's a curved surface too, over the top, the air is being pulled downwards over that curve over the wing. So again, you get an opposite force upwards. And that opposite force, what's it called? Lift. Lift!
Yes.
And that's what keeps your airplane in the air, and that's what keeps the ball hovering over the end of the straw. Unfortunately, because the airplane's moving very quickly through the air, that air will keep going and keep that lift generated, whereas we're having a little bit less success with keeping the airflow going and keeping our ping-pong ball in the air.
Lift.
So that's how you can show how an airplane wing works with a straw and a ping-pong ball.
Wow.
Yay! And a round of
Thank you very
applause for our
much,
little
guys.
scientists. It's showtime.
702 and Cape Talk.
The Naked Scientist.
Okay, Aki, I thought you disappeared again, but you haven't. I beg your pardon. We've got a question, and then we'll get on to our next experiment.
Who had their
Who's
hands
asking?
up for a question over here? Here we go. There you was. What is your question?
How did dinosaurs become extinct?
Okay. If you didn't hear that, how did dinosaurs become extinct?
Well,
really still
we think that, or at least we have evidence that dinosaurs disappeared about 60 million years ago. So there were lots and lots of dinosaurs around from about 300 million years ago. That's when crocodiles actually first evolved, until 60 million years ago when dinosaurs abruptly disappear. And we know they abruptly disappear because you can see fossils spanning all of that time, and then the fossils of dinosaurs from 60 million years ago stop appearing anymore. So something catastrophically happened to make the dinosaurs almost vanish overnight. Why do we think that happened? Well, there's a number of theories, and probably it's a combination of factors, but we think that effectively climate change was what was responsible. What caused the climate change? Probably two things. At the time, about 60 million years ago, there were periods of very intense geological activity on Earth. There were some parts of Asia where there were some massive supervolcanoes that were ejecting huge amounts of material into the atmosphere, and this dust would have effectively changed the world's temperatures quite radically. And this would have made the world a much less hospitable place for dinosaurs to live, because dinosaurs, being effectively reptilian, they're cold-blooded, they find it harder to control their body temperature than we warm-blooded animals do. So they would have found an Earth with a rapidly changing climate much harder to cope with. The other thing that we know probably happened is that there was a very big impact with the planet about 60 million years ago. A fairly massive object came in from space and slammed into the surface of the Earth down near Mexico and the peninsula in South America. And we can see there's an area of the Earth's surface there where there is the remains of this crater, which can be detected in terms of you can actually physically see geology corresponding to where this impactor would have smashed into the Atlantic Ocean. And that impact would have ejected huge amounts of dust and other material into the atmosphere, and this too would have provoked quite intense climate change. A more interesting question is where did that impactor come from? And there's a researcher in America I spoke to a few years ago called Bill Bottke. He's in Arizona. And they've actually done almost like a meteorite post-mortem to work out where the object was that came into the Earth. And they have found evidence of the source of that impactor in the asteroid belt. So out between the orbit of Mars and Jupiter is a big ring of material, which is a failed planet, if you like. At the time when our planets were forming, about 4.5 billion years ago, there was material that was coalescing to grow into planets. And because Jupiter and Saturn are big and have very big gravitational influences, they stopped a planet forming in that part of our solar system, so there's just a bunch of rocky rubble left over there, and that's the asteroid belt. And some of those asteroids are being nudged a little bit by both the gravity of the big planets, but also light. And big words coming up. There is a phenomenon, and this is impressive, right? It's called the Yorp effect. Yarkovsky-O'Keefe-Radzievsky-Paddock effect. Okay?
Oh, we all knew that.
I'm just reminding you. It's useful to. And this is where, when photons of light hit a surface, because light has energy, when it is brought to a surface, it arrests and it imparts that energy to the thing it hits. This will give a push to that surface. So objects in the asteroid belt which are being illuminated by light from the sun are constantly feeling a little nudge from light, and we think that this dislodged something caused something else to smash into something else, dislodging the object that then became the impactor that 60 million years ago ultimately collided with Earth and did for the dinosaurs.
All right. And it might not have done for all of the dinosaurs, though, hey, because it's believed that modern birds are actually the descendants of a group of dinosaurs called theropods, which included the ferocious T-Rex. So there you go, T-Rex was just a big chicken.
Yeah.
The next experiment, Chris, are we ready?
Right. Well, it's a beautiful sunny day outside, so we thought we'd do something about the sun. We don't get much of that in the UK, so it seemed appropriate to visiting Johannesburg. So does anyone know what the sun is made of? Yeah? Hands shot up over here. What's the sun made of?
Who knows what the sun's made of? Put up your hands.
Okay, we all want to hear. Aki's going to tell.
Fire. Energy.
Hydrogen and helium.
There we go. Hydrogen. Right. Energy is a really important part of that, but hydrogen, absolutely. And how do we know what the sun's made of? Can we go there and measure it? It's too hot. So, but we can actually tell because every single chemical has a signature color. And the reason for this, the reason that we can see this, and we can see it in the sun, is because that so much heat energy is being given to that hydrogen that it gives off its signature color when it re-releases that heat. And we can actually show this with a lighter and some chemicals that we have. We're going to make some little alternative suns here out of these spray bottles. Right. So the reason every chemical has a signature color is because, are you all familiar with the fact that elements are made up of atoms? Elements are atoms. So we have a nucleus in the middle, a very positively charged nucleus, and then surrounding that a cloud of electrons. And the reason for the chemical properties of these atoms, the different chemical properties, is because those electrons can only sit in certain energy levels in that cloud. Now, when you give an atom of an element energy, those electrons, some of those electrons can jump up to a higher energy state, but they have to go back immediately to where they started because they can only sit in a certain place around that nucleus. So that when they jump back, the distance that they jump back to exactly where they started and sort of reset that atom, that equates to a wavelength of light. So it gives off a color of light. A particular wavelength equals a particular color. So you can see what's happening, measure that energy state jump and therefore see what element you're seeing by seeing the color it gives off when you give it heat and it releases that energy. So here's our heat energy. Here's our little tiny sun, which is a lighter. And first of all, we have copper. We got a solution with a little bit of... So can we drop the lights as much as possible? So hopefully we'll be able to see our little flame experiment and hopefully not set lights to the studio. I notice Aki's keeping a very safe distance from this one.
I'm scared of
Okay, so can you all see our flame? So we're going to try this. So this is copper. Does anyone know what color you should be seeing when we give this heat energy? Green or blue? Okay. Would help if we could spray our copper.
There.
Can you see that? Can you see, what colour is that?
Greenish blue.
Greenish blue.
Yeah.
So there we go. So that's the wavelength that we've got from copper. Now the second element we've got is strontium, which is used a lot in fireworks. Does anyone know what colour we'll see when we spray this strontium through this flame? Red. Let's see.
Orange.
Have to give it a little bit of a kickstart.
Yay.
There we go. That's a bit more effective. That's a bit more flammable. What colour are you seeing?
Orange, reddish orange.
That's red, and we've kind of killed our lighter. Oh, it's still working. This plucky little lighter is still going. Now, the third one is sodium. Does anyone know what colour we'll see when we spray sodium through this heat? Orange. It should be. So hopefully we've made this flammable enough. I'm spraying it towards Reedy over here, so keep your distance.
I smell divide.
What colour? Shout out the colour.
Oh, it's like fire yellow.
There we go.
Whoa.
What colour?
Orange.
So there we go. That's how you can measure what the sun's made of.
That is very cool. Very cool. All right, we've got a quick question, Reedy. You had a question. Your name and your question.
I'm Jackie. How does the human brain works, and why is that some of the people happen to be intelligent than others? And I want to know whether is it genetically that maybe some of the people are smart, and is there any scientific difference?
Okay, one question.
So you want to know what's the difference between Chris Smith and myself? Someone is intelligent and someone is not intelligent, right? Are we born like that, Chris? Why are you smarter than me?
No, I thought you said, what's the difference between Chris Smith and Aki? I was going to say about 15 stone.
About 100. IQ of about 160. IQ of 160 is the difference, I'd say.
How does the brain work? Well, the brain is full of nerve cells. There's about 100 billion of them. So that's 1 followed by 11 zeros. And each of those makes, on average, 1,000 connections to other brain cells. So there's perhaps 10 to the 14 connections between cells. And these nerve cells are having chemical conversations between themselves. So when one nerve cell becomes active, it sends a message down a very thin structure called an axon, which terminates on another nerve cell. And when an electrical impulse goes down that axon, it reaches the connection and makes a bit of chemical get squirted onto the target nerve cell. And those chemicals that come out can be either excitatory, they can stimulate the target nerve cell and make it more active, or they can be inhibitory. And this means they can turn off the target nerve cell. So your brain is working not just in excitation, but it's also working in inhibition. So you've got things being turned on and things being turned off. And you can tune those circuits. So when I want to make a memory, for example, I take a set of nerve cells and I can adjust the strengths of the connections to other target nerve cells and make a circuit so that when a certain stimulus comes in, certain other nerve cells in that circuit light up. So at a basic level, the brain is just nerve circuits, and there are different parts of your brain that are specialized for doing different jobs. And we can tell that because you can put people in a brain scanner and you can measure the activity of certain bits of the nervous system when you get someone to do a certain task in the brain scanner. You can ask them, for example, to move their right hand, or you can ask them to think about playing tennis. And this elicits activity in the brain in the areas corresponding to control of those tasks. So we can begin to work out what bits the brain does, what bits the brain do what. The problem we have is that we don't actually know how that, when brought together, corresponds to consciousness. We have no idea why we're conscious. And in fact, neuroscientists for many years have described this as the hard problem, which is probably a little bit of an understatement, to be honest. But we have no idea what consciousness is. Or, for instance, I'm looking at you lot here. It's a lovely view. But I feel like I'm seeing you in front of me. Actually, you are appearing to me and to my consciousness right at the back of my head, in my visual cortex. And a message is being taken from my eyes and presented to that part of my brain via the optic nerve. But my consciousness says you're right in front of me. The other rather bizarre thing is that you are experiencing, and I am experiencing, the world with a time delay of about 1/3 of a second. Because the time it takes my consciousness to process the information coming in and for me to become aware of it is a time delay of at least 1/3 of a second. And scientists did an experiment a few years ago where they gave volunteers who didn't know that this was what was being done a controller for a slide projector. And they said to them, show yourself some slides. What they didn't know is that there were no batteries in the controller. What the scientists were doing was measuring the brain waves of those people from the area corresponding to the movement of their fingers, so they could tell when the person was planning to move their thumb to press the button to move the slides on. And they were then able to turn the slides on using the computer reading the brain waves. But they asked the people afterwards, did you notice anything strange? And the person said, yes, it was almost like the slides knew when I wanted to change them, because they could tell that it was happening almost faster than they wanted it to happen. In other words, the people were not conscious of their own intention to move the slides forward until after it had already happened. Isn't that bizarre? We're all living in a world that's 1/3 of a second slower than we're conscious of it. And when you watch sportsmen or sportswomen playing fast sports, those people at Wimbledon, they're processing and making movements for reacting to the ball coming over the net and hitting the ball back. They're working faster than their visual system actually can present that information to their consciousness. They're not aware consciously of how they're responding to hit the tennis ball back. And what's happening is they have very fast brain circuits that are responding just to the visual stimulus of a ball coming onto their eye, and they're executing it through another part of the brain that does not present it to consciousness, which tells your motor system this is what you have to do. And it's only later that they know whether or not consciously they hit the ball.
Sure, that's amazing. Would that experiment explain why Aki's always late with his traffic reports? You know, it's just that...
Oh, that's a low blow. Do you agree with me, folks?
Unfortunately, we don't have time for more questions. Can you believe it? We've been doing this for an hour and it's gone by so quickly. Chris, thank you so much for joining us. thank you very, very much. It was lovely to have you. And you left that smell.
That's your perfume, really.
So you and I, Victoria, you and I need to talk.
Just for clarity, when Reedy says we left a smell, this is the smell of Victoria's experiments. We don't have a problem with hygiene. Okay.
I can testify. Well, if you want to go see The Naked Scientists, you've got that opportunity at the Rand Easter Show. What can people expect, Chris?
Okay, we're going to do 3 shows a day, actually. We're going to do 2 runs of our crisp packet fireworks, what we're calling Eureka Show, where we're going to do a whole load of linked experiments, which include quite a few gratuitous explosions. So if you have explosive persuasion, do come and see those. And then in the middle of the day, we're going to do something similar to what we've been doing for you this morning here on Reedy's show, but it's, again, an opportunity to ask and potentially answer any science question on anything. But we're going to add the added twist that we're going to make it harder and harder as the time goes on by reducing the amount of time available to answer each question down to perhaps 45 seconds for an answer. So it makes me work very, very hard. So come and join in, and we would love to have your questions. But can I just say thank you very much, everyone, for coming. Thank you for listening to this programme for 8 years. We've been doing this now. It's 8 years. And we really, really enjoy coming to South Africa, and not just because the sun shines, but because we get such a warm and wonderful reception, and we really like meeting you all. Thank you very much for having us in your ears and in your cars every Friday morning when we're not here.
No, thank you, Chris. Thank you very, very much for all the time that you give us every single Friday, and we know that this is a very special segment for our listeners and for us here as well. Chris Smith and Victoria Charlton, everybody! Right now...